Thank you. A couple things before I begin. First off, I'm not Mr. Freeze, okay? My real name is Jerry Zimmerman. I'm a physicist at FermiLab. FermiLab's a national lab run by Department of Engineering. By the way, kind of odd timing, I guess. This is actually our 50th anniversary also. We're having all kinds of special events this year. In particular, I'm telling you to mark your calendar. September 23rd is a big event at FermiLab. It's our open house, a big open house for the public. Lots of area labs will be open to the public that aren't normally open. This is a chance for you to come visit FermiLab, so mark on your calendar September 23rd. In particular, quickly, as I said, I'm a physicist at FermiLab, and if you've ever seen The Big Bang Theory, okay, I am more the Leonard Hofstadter compared to the Sheldon Cooper type physicist, you know. Except for I don't have a really hot girlfriend, so that's kind of a... But the area of science that I work in particular, is called cryogenics. Now, cryogenics is not the science of crying. So we know crying during this demonstration, but it is the science of the extreme cold. And before I start horsing around, I always like to give you a chance to see what I'm working with. We sometimes refer to this stuff as liquid air, but technically this is only a portion of the air. This is liquid nitrogen. That's it. It's just a clear liquid. In fact, if you didn't know better, you could actually very easily mistake that stuff for water. Now, there's a few things that we notice right off the bat that do seem a little different. First of all, what's this stuff coming off here? Smoke's hot. What's this stuff? See, the balloon guy even got scared. So what are they? It's water, it's fog. Just like you see a breath in winter, same effect. Only this is caused by the fact that the liquid in the bag is so cold that it's condensing the water vapor out of the air around us. What's happening to the liquid in the bag? It's bubbling. It's bubbling because it's boiling. It's boiling because everything's so hot that everything makes it boil. My glove is so hot to that liquid that my glove makes that liquid boil. Just like an electric iron makes water boil, my glove makes that liquid boil. Well, here's where you help me out. If you want to know something, what do you have to do but ask a question? As I go through the show, I'm going to regularly go like this, and what I want you to do is ask me the question, how cold is it? So let's give that a try. It's so cold, it makes a snowman shiver. No? It's so cold, it turns Smurfs blue. It's so cold, it gives frostbite to a polar bear. Okay. What you actually need to know the temperature of something is a thermometer, and I have a thermometer about 68, very nice in here. But actually pour this liquid on my thermometer, so I can actually measure a temperature liquid. So I'm pouring my liquid right on my thermometer like that. So I measure what temperature that liquid is really at. So liquid nitrogen is about 40 degrees. No, what happened? I didn't break my thermometer. The thermometer is working just fine. What it's actually measuring is minus 320 degrees. That's how cold this liquid is in these containers. And because it is so cold, it has a very powerful effect on lots of things. Now, one of the first things that we noticed was that the liquid was boiling. When you boil water, you get steam. This isn't water, this is nitrogen. So what am I going to get when I boil nitrogen? Nitrogen gas, or basically air. So I put a little in the bag, seal the bag up. What will happen is that bag will fill with nitrogen gas. Did I seal that? No. Yeah. No, there, oh. Okay, I guess this bag really wasn't big enough for this job, so I'm probably going to need a bigger bag here. Actually, before I continue, I am going to need a little help with some math. So I'm going to give everybody a little mental math exercise. It's a very simple problem. Should be able to figure this one out really easily. Now, I have 24 inchworms. So tell me, how many feet does that give me? How many feet does 24 inchworms give me? 2? I'm sorry, you're wrong. Why? Because worms have no feet. You get 0 feet. Oh, boy. Gee. So I got a bigger bag here. Now, one of the things I could be doing as I do this demonstration is a little scientific investigation. That investigation is what we call the expansion ratio. Basically, how much gas am I going to get from a given amount of liquid? If I start with, say, 1 cup of liquid, how many cups of gas you get? Well, the way to find out, of course, is you take 1 cup of liquid, you put it in your bag, you seal your bag up, and you'll see how many cups of gas you get for each 1 cup of liquid. Now, this is a good sized bag. I'm kind of use this table here as a hot plate warming it up for me. So what do we think? Is that bag going to be big enough to hold 1 cup of liquid, converted to gas? Yes? No? No. Okay. So tell me, what do you do when you have a little scientific setback? Do you give up? Do you quit? No! You buy a bigger bag. So we repeat our experiment. We start with 1 cup of liquid again into the bag. Now, the good thing about this bag is that I know this bag is, in fact, a 45-gallon trash bag. This bag here holds 45 gallons. But wait a second, I don't need to know how many gallons of gas I get. I need to know how many cups, because I'm trying to make a ratio of cups to cups. So I guess I need to know how many cups are in 45 gallons. Well, I guess first I need to know how many cups are in 1 gallon. So how many cups are in a gallon? 4 quarts, 8 pints, we'll get there eventually, right? 16 cups per gallon, 45 gallons in the bag. Okay, 16 times 45, that's a little tricky here. Is this bag going to be big enough to hold 1 cup of liquid, converted to gas, 16 times 45, going once, you gotta read. 16 times 45, going twice. And the question, is this bag big enough to hold 1 cup of liquid, converted to gas? And the answer is yes. In fact, this bag is just big enough to hold 1 cup of liquid converted to gas. For the actual numbers, for every 1 cup of liquid nitrogen, I get 700 cups of gas. By the way, 16 times 45 is 720, so this bag is, why doesn't that bag float? See, it's not helium that's lighter than air, it's nitrogen which is there. So this is like a big beach ball, like a helium balloon. Now that's fine, but that's not very convenient. It'd be much better if I, actually had a container I could hold it in. Now, because I am kind of the clumsy sort here, I have to make sure that I put a cork on that so I don't spill any of it. What? Is there oh, God. Oh, that's what happened. Oh, yeah, that's what happened. Okay. Actually, by the way, this is kind of a neat way to demonstrate another principle of science. And that's if I kind of turn things around a little bit and do it this way. Exit stage left. So what principle of science was I trying to demonstrate there? Rocket propulsion. The reason why the bottle flies away, because it is just like a rocket and the cork comes off. But the truth is, that's still really not what we would do. What we'd really do, this. What happens in this case? The bottle blows up. Yeah, in fact, I know somebody at FermiLab, when they did this demonstration and the bottle blew up, it broke his nose. Good seats in front, right? But wait a second, why would somebody knowing the bottle? By the way, it doesn't have some sort of nose radar, okay? It could hit you anywhere. Oh, wait a second, why would somebody knowing the bottle's going to blow up be standing here holding it? See, one of the things about working in science is understanding how to handle things safely. So how do you prevent the bottle from blowing up? You hook a hole in the lid. Oh, by the way, bazinga. It's the only thing I've learned from that show, by the way. So we say investigate the gas expanding. Now we're going to investigate what happens when you introduce a gas into it. What's going to happen to a balloon? Whoops, a balloon. It's going to pop. It's going to freeze. We'll find out. Put it in here and see what happens. Oh, this is quite interesting, yeah. It's going to change color. Oh, wait a second. No. It's going to change shape. That's not it. Okay, wait a second. There seems to be a... No. Okay, wait a second. No, that's not it. Okay. No. Okay. Let's see here. No, that's not it. Okay. No. Okay, how about... No, that's not it. Okay. Is that... That's definitely not it. Okay. Is that... Let's see here. Is it... No, let's see. There it is. Okay, no. Okay, there it is. Okay. The air inside those balloons collapses that 700 times, shrinking down to 10. Once you bring the balloons out, the air inside warms back up, re-expanding, re-inflating to the same shape and size before we started. That's the reason why all these balloons are able to fit inside containers, because the air inside had collapsed that much. Oh, by the way, in sort of an odd timing thing, I recently just got done working on an experiment at FermiLab, and this is the truth, okay? The name of that experiment is called the dark side. I was working for the dark side. It's hard to recruit people to work for the dark side, by the way. It's actually a cryogenic detector in Italy. If you decide to Google that, you need to Google Dark Side 50, otherwise you'll never find it in a million years. But when I was asked to join that experiment, I was told it was going to require some long hours, some weekends. And I said, okay, if I join your experiment, what do I get out of it? You know what they said? They said they'd give me a lightsaber. I was expecting something other than a very, very lightsaber. By the way, I don't understand. These can't that dangerous. I don't know what the big deal with these lightsabers being so dangerous is. Oh, by the way, this is good for something. It's very good at making cold cuts. Oh, by the way, you do know what this is, don't you? A hot? You're not watching. What's a cold dog? It's a chili dog. Never mind. I was going to use. Go back right there. I was going to use this balloon. Oh, it doesn't fit. Oh, wait a second. What if I help it along? As the air inside that balloon cools down, it collapses. Remember from the movie right by now, she's saying, Dorothy, you wicked little girl. As the air inside that balloon cools down, it collapses by the container. An even more rigid container, regular bottle, has a regular cap. You've seen this in the Pepsi commercials. The air inside that bottle collapses, causing the bottle to collapse that way. You'll notice when I'm working up here, it does kind of look like I'm reaching in these containers, and I can actually see where the liquid is inside containers. I have different things for different jobs. I have these blue gloves. These are special cryo handling gloves designed to handle extremely cold things. I have the tongs, very good for taking balloons in and out of liquid nitrogen here. But you'd think the hazard of this stuff is that you wouldn't want it to get on your skin. So you'd wear some type of protective gear to protect your skin from contact. Now this black glove is perfect. This is a special glove. It's kind of expensive because it has been guaranteed tested liquid tight. So so no liquid can get through this glove onto my hand. So like this glove is perfect for me to reach in and grab some. Is this a bad idea? I mean, what's going to happen? Like my finger's just going to bust off? No, I didn't actually lose any fingers in this demonstration. But this glove isn't very good at working in cryogenics because this glove itself changes into something that's, in fact, much more like glass. In fact, why do you think I'm wearing this white glove? Because of the cold temperatures? No. Because if I did that with glass, what would happen to my hand? I'd cut my hand. Do you know how hard it is to explain to people how you cut your hand on a rubber glove? So show me a piece of white glove. How'd that start? It was really sharp before. But what would really happen if I put my hand in there? If I put my hand in there for a few seconds, I'd get in my hand what is called a cryo burn. Very similar to a fire burn, same body physiology going on. In fact, a few minutes later, all the skin would peel off my hand. Because it burned the skin off the hand, same as sucking in fire. Actually, my hand in there for about 5 minutes, it would freeze solid. Now, as compared to those TV shows and movies you've seen, you do not shatter like glass. That's not the way the body is. The bones stay about as strong as they are now. But having said that, what in the world would I be thinking of? Holding my hand. Why can I not put my hand in the container there, but I can hold in my hand here? And I can kind of demonstrate that by doing this. You scoot this stuff back just a little bit here. What happens when I pour this liquid on the table, it goes running off the far side of the table. Reason it runs across the table that way is the same reason why I can hold it in my hand. See, if I was using a different liquid, let's say I was using water, and poured water on my hand, what would my hand get? What would the table get? Hand's not wet, the table's not wet. So what happened here? That liquid did not touch the table, did not touch my hand. My hand and the table are so hot that it's boiling before it reaches the surface, forming a layer of gas. In case the table is making a layer of nitrogen gas, it is right on top of. In case my skin, it's not contacting my skin to transfer the cold temperature to me. It's actually called the Lindenfrost effect. I've heard other people pronounce that differently, but real hazard liquid nitrogen is not your skin. The real hazard is in something that can actually absorb a liquid. This cloth is wet with nitrogen. If that cloth against your skin, you transfer the cold temperature to you. Ever go to a doctor and get a wart burned off? What they use is a cotton swab or a Q-tip to transfer that cold temperature to give you the burn to try to get rid of whatever you're trying to get rid of. I quite often get asked, by the way, a little background information. FermiLab allows me a couple of days of my work schedule to go to area schools and do this demonstration. That's the reason I'm Mr. Freeze, to promote science in the classroom. But I usually get asked whenever I do one of these demonstrations for schools, can I do that? And if you notice, okay, when I do this, I'm very careful not to toss it where I get on myself or toss it where I get on somebody else. See, the only way I can actually teach somebody how to handle ignition is what? Is if everybody in the area is naked. See, if you weren't wearing any clothing right now, this would be a perfectly safe demonstration, right? Oh, wait a second. There's something else on your body that absorbs liquid, isn't there? Hair, yeah. See what happened to me? No, there's nothing to do with working on ignition. This is pretty neat. Oh, by the way, real quick, you do understand, you do realize, this is STEMCON, okay? There is a real reason why they call it STEM, S-T-E-M. Now, the letters do stand for science, technology, engineering, math. But the reason they're in that order is because we consider science and math kind of to encompasses all the things that go on in technology and engineer. So there's S-T, and there is the other reason, of course, is that nobody really likes the Mets. Okay, that joke isn't very good for New York, but it works out here. This is pretty neat stuff. This here is a 4-liter door, 4LD. Now, 4 liters is about, how much in U.S. terms? It's about a gallon of liquid nitrogen. So how much do you think a gallon of liquid nitrogen costs? Is it like, $5 a gallon? $10 a gallon? 20? Try $1 a gallon. In fact, in really large quantities like we get at FermiLab, we actually get liquid nitrogen for 25 cents a gallon delivered. So why is it so cheap? First of all, where do we get it from? The air. All nitrogen I'm throwing around here, it's going in the air. You're breathing it all in. If you be so kind as to breathe it all back out again, at the end of the demonstration, it's just recyclable. Secondly, what do we really need out of the air? Oxygen. Liquid oxygen, much more valuable, much more nitrogen than the byproduct. That's a good thing it is so cheap. We do use a lot of it there at FermiLab. Ever seen those big trucks go down the highway? Each one of those trucks holds 7,000 gallons. We use 3 of those trucks every day. But you know, if companies use more than we do. In fact, you've eaten their stuff frozen in liquid nitrogen. They probably should put a sign on the door right next to the clown's face. Yeah, Ronald McDonald used liquid nitrogen to freeze that hamburger he ate last week. Ever wonder why it looks the way it does? Now you know. It's not all bad. Okay, first off, it's 25 cents a gallon. You can freeze a lot of hamburger for 25 cents. Secondly, it's just nitrogen. If you can dump a truckload of stuff directly on the food, it will not affect the quality or safety of food. If they used a CFC refrigerator like you have at home, or an ammonia refrigerator, both those contain chemicals that are harmful to the food or to the environment. And the third reason the McDonald's Corporation does it, I can demonstrate this way. I'm going to take and put some water in this bag, and now I'm going to add some liquid nitrogen. Now, this is kind of interesting demonstration in and of itself. I have in this bag 2 liquids. One liquid is boiling, while one liquid is freezing. One liquid is going from a liquid to a gas at the exact same time as another going from liquid to solid. So which one is boiling? Nitrogen. Which one's freezing? What am I making? By the way, it's so cold it makes ice scream. Oh, that came out wrong. Not ice. Screaming ice. We just turn around the other way. By the way, isn't that what you get when you pinch Olaf? Screaming. Oh, never mind. Now, this ice I'm making here is regular standard water ice. Very odd shape because of the way it was formed. But it also has the property to get a little smaller piece. If this ice is so cold, it freezes to your skin. It's so far below 32 that it freezes to me before I melt it. Same idea as sticking your tongue into a flagpole in the winter. Don't do that again. I said again, right? If you do, I will show you that movie again, and again, and again, and again. So what would happen if I tried to eat that ice? Freeze to my tongue would be pretty painful, yeah. So what in the world would I be thinking of? Oops. With a marshmallow. Obviously don't have a campfire up here, so I have to use the next best thing, which is, of course, liquid nitrogen. So now the question is, what do you do with a very well frozen marshmallow? Some of you may have stopped by our booth there and had a chance to try that out. But so what do you do with a frozen marshmallow? Now, some people will suggest I make s'mores. The problem is s'mores are supposed to be mushy, and this is no longer mushy, it's now crunchy. So now the question is, what do you do with crunchy marshmallows? And I am kind of hungry, surprisingly. But if you don't mind, I'll just kind of have this as a snack. I'm sorry, I should not be smoking in front of you kids. Well, that wasn't smoking, that was fogging. It's okay to fog. But wait a second. Why was I allergic to marshmallow? One of the things about marshmallows that most people don't realize is that marshmallows, in fact, are extremely good insulators. What insulators do is they don't transfer temperature well. That's why you insulate your house. Well, marshmallows are almost as good as the insulation you have in your house. Don't go home and insulate your house with marshmallows, all kinds of double hands. But a marshmallow is such a good insulator, it will not transfer the cold temperature of liquefaction to me well. So even though it's just as cold as the ice, I can take it out and eat it, and it will not give me a burn. Ice isn't near as good. Will transfer the cold temperature fast enough, give me a burn, be very painful. Now, I quite often get asked, whenever I do one of these demonstrations, why in the world do we use so much liquid nitrogen in their FermiLab? And I can demonstrate that with this. I have here an electromagnetic coil, and there's a law called Lenz's law that anytime you put an electrical conductor into a changing magnetic field, it produces a current in that conductor, and that current produces a magnetism that's opposite to one it's in. So in this case, when I activate the coil, now that's good, but we at FermiLab would like our electrical conductors and our magnetic fields to not just be good, to be really good. So how can we make this a better electrical conductor? By doing this. By cryogenically freezing it, it becomes a better electrical conductor, and therefore produces a, oh, by the way, it's so cold it gives goosebumps to a penguin. It's so cold it gives a slushy brain freeze. It's so cold it gives you brain freeze just thinking about it. Okay. So now that my ring has been cooled down to the cryogenic temperatures, it now is a better electrical conductor. And when I put it back into the same magnetic field as I had before, it now goes much higher. The reason why that goes higher is because it's producing a higher current and therefore more magnetic field. Oh, by the way, if I let this sit out here and warm up a little bit, will it go higher or lower? Lower. So you could actually use it as sort of an odd thermometer. By how high up it goes, you could actually tell what temperature it is, and therefore you could use it as a thermometer. So, okay, any quick questions before I see if I can answer any questions you have? No? I'm either terrible or great. I'm never sure which. Yeah. Okay. So let's go ahead and get it. Next thing, we're going to do a little experiment. We're going to do a little background demonstration first. I have here a racquetball, a tennis ball. You can actually hear something quite unique in this setting. Let's see. Listen very carefully. Racquetball. Not that much. Tennis ball. That popping sound you heard was actually thunder. Thunder. How could that be thunder? What thunder is a sonic boom caused by air expanding faster than the speed of sound. Case of a lightning bolt is the heat of the lightning bolt caused the air to expand so fast. In this case, the cloth covering the tennis ball caused the nitrogen to expand so fast to exceed the speed of sound expansion, causing a sonic boom that you hear as thunder. Now, I do this as kind of a background demonstration, but it's kind of interesting by itself. Ever wonder why certain sports don't catch on really big in certain parts of the world? This is a good example. Racquetball in Alaska is not a good idea. I don't recommend it. Hit by that, you're probably going to be sorry. The Alaska Open, not one of those big tour events on the old tennis circuit. Hit by that tennis ball, you probably, actually in Alaska they do not call it tennis. Do you know what they call it? Dodgeball. Hit by that ball, you're out. You're going to a doctor, hospital, something like that. But now I do that as kind of a background demonstration. And whenever you're doing a science experiment, what you're actually trying to do is answer a question. In our case, our question is, what do you think is going to happen to this ball? Now, before you do your experiment, you come up with your hypothesis, your educated guess. In our case, we could look at similar examples. We did a balloon. What happened to the balloon? Collapsed and came back. We did a racquetball tennis ball. What happened to them? They got hard. So what do you think's happened to this? Is it going to collapse like the balloon or get hard like a racquetball tennis ball? How many say it's going to collapse like the balloon? How many say it's going to get hard like a racquetball tennis ball? How many are not voting in this election? I didn't like either of the candidates myself, so that's okay. So do our experiment, see what happens. Now, the reason why the balloon collapses is the air inside the balloon collapsed. Does this ball have air inside of it? Yes, it does. Well, it didn't collapse. It got hard like a racquetball tennis ball. Okay. But what happened to the air inside that ball? Did it still collapse? Yes, it did. It had to. Because it got cold, it had to collapse. So now I have a hard brittle exterior with a collapsed gas or vacuum inside. What does that make this like? No, I'm not voting. I'm pointing to a light bulb. What happens to light bulbs when you hit them? They explode. Reason why that ball explodes, because it is just like a light bulb. When you hit it, it implodes into 1,000 pieces all over the place, just like a light bulb would explode. Okay. Okay. This next one. This is, if you ever go, let's see here. No, okay. This is for you ladies. No, I'm not giving you flowers. But you ladies should know the connection between flowers and cryogenics. And it's something about flowers you like. They smell nice. And if you want to smell as pretty as a flower, you take a flower base and rub it on your cheek. Give you rosy red cheeks. Well, if you start with a red rose, right? But wait a second. Where do you get that pretty flowery smell? Perfume. But how do you get the pretty flowery smell into the perfume? They do it this way. By cryogenically freezing the flower. All the fragrance gets locked in the petals. Then the flowers can be taken out. The petals can be crushed. The fragrance processed into perfume. Most flower-based perfumes use cryogenics to process the fragrance out of the petals. Oh, by the way, it's as cold as the heart of a guy that would do that to a flower. Oh, it's as cold as my heart. Oh, that's not good. Wait a second. Okay. So, okay. I think you're ready for this. Actually, if you could just wait a second. I'm a little thirsty, so if you don't mind, I'm going to drink of my pop here. Oh, you know what? My pop's warm. I don't like warm pop. Oh, wait a second. I got this. See, I got this little thermos here. You know what I can do? I can take and put some of my liquid nitrogen stuff right in my little thermos like that. Then I will take my pop, put the cap on. In just a couple of seconds, I'll have a nice cold pop. This will be great. It's only going to take a couple of seconds for that to get nice and cold. So that'd be... Well, the good news, it's cold. Oh, but now it's flat. I don't like flat pop either. By the way, if you're wondering what happened, at the point the pop reaches its freezing point, all the carbonation comes out of the liquid, causing it to come... Hey, wait a second. Is that the reason why they call them fountain drinks? I mean, I've never seen a fountain... Oh, never mind. By the way, kids, you want a fun experiment to do at home. On a very cold winter morning, take a bottle of pop, poke a hole in the lid, set it out in your driveway. In about 10 minutes, it'll do exactly that. Do not do that in your mom and dad's freezer. I'm not responsible for the mess outside on a cold winter morning. So, let me explain what's going to happen here and what happened to that poor guy at FermiLab I know. Basically, what he did is he took, let me find, hang on, it's in here someplace, I know it is. Maybe not. And, nope. Okay. He took one of these little bottles. He put some liquid nitrogen in it, put the cap on it, threw it in a trash can, stepped back, waited for it to go off. And he waited. And he waited. And he said, I must have done something wrong. So I looked at the trash can, see what was going on. That's when the bottle went off, hit him in the face, broke his nose. What he didn't realize is how long these take to go off and how powerful it is. Without any help, this bottle takes 3 minutes to develop enough pressure to explode. When it goes off, it has over 250 psi pressure. That's what this bottle is designed to withstand. Well, when I was trying to figure out how to do this demonstration for schools, I can't wait 3 minutes to see if the bottle's going to go off. So to come solution to this 3-minute problem. The solution is pretty straightforward, and I actually already showed you. What can I add to this bottle to make the nitrogen boil faster? Water. You saw in the Ziploc bag, this now makes the nitrogen boil so much faster. Then now this bottle will take about 15 seconds. Now 15 seconds enough time to put it in the can in there, step back, but in so long to wonder if it's actually going to go off. Now a few things I need to advise you of. First of all, that 15 seconds is only an approximation. I cannot count down 5, 4, 3, 2, 1, have it go off. I mean, these bottles aren't manufactured at a huge level of precision. Secondly, when it goes off, it is extremely loud. So if your ears are sensitive to loud noise, you want to put your hands over your ears. It's safely loud, but it is extremely loud. So now, I need to be absolutely positive about just one thing, and that is, are you ready? Yeah. Okay, well, we'll see. Okay, now that 15 seconds does not start until after I put the cap on the bottle, because that's when pressure actually starts building in the bottle. So until that time, there is no hurry. So it's not until I do this that now I have 15 seconds, and I cannot stop it. Whew. Okay. The rest of the bottle go down there, is it? Here. Okay. This is all that's left of that poor bottle that gave its life for this demonstration. As you see, it didn't survive it all too well. Secondly, it always amazes me, no matter how many times I do that, I'm always able to hit that confetti bird that's flying overhead, just knock him right out of the sky every single time. It's just amazing. Now, I've been asked to do this show in venues that do not allow me to shoot a cannon off. I do a show in IIT at Wheaton every year, and every year I do a show, I actually blow a hole in their ceiling. It's even more amazing. They actually invite me back every year, so it's even more amazing, I guess. But I tried to come up with a solution to play where I cannot always use a cannon. Well, the solution to this problem is pretty straightforward. Instead of using a cannon, I use a cardboard box. Now, the advantage of the cardboard box is it doesn't shoot up, it explodes out. The other advantage of the cardboard box is because it's made of cardboard, an absorbent material, I can actually use a little bit bigger bottle and basically end up with the same sound level explosion with a smaller bottle in the cannon. But in certain situations, with certain groups of people, I'm not even limited to the little bit bigger bottle. I can actually use the lot bigger bottle. Now understand, the bigger the bottle, the louder the explosion. So I will leave it up to you. How many of you would like to hear the little bit bigger bottle? How many of you would like to hear the lot bigger bottle? I will never be able to get rid of this bottle, by the way. I just don't understand. I just try, and never seems to be. Now, somewhat surprisingly, almost everything remains the same. I still add water to this bottle to make the nitrogen boil faster. I still add the liquid nitrogen, and in about 15 seconds it goes off. The difference being, of course, instead of shooting a cannon off, it's going to blow that cardboard box to pieces. So, I need to be absolutely positive about just one thing, and that is, are you ready? You're more ready this time than last. All right, that's good. Okay. Okay. Let's see here. Okay, here we go. Let's see. Here's one little piece of it. Here is another piece. I'm never quite sure how this got over here because there's so much. Where did it go that it actually got over there? I'm not sure how that worked. But this is all that's left of that poor bottle. Where is it? Oh, there we go. I have one more demonstration to do, and thank goodness this one is not loud. But the reason I do this particular demonstration is that I cannot legally transport the liquid nitrogen that's in these open containers. It is too dangerous to transport it this way. So I had to come up with a solution of what to do with this nitrogen. Well, the solution to this problem is pretty straightforward and pretty neat, actually. Actually, could I have a volunteer from the audience? Let me see here. Hang on. You want it? I have here a bucket of water and some soap solution. And Iris, if you could put a little bit of soap solution in the bucket of water, so you do that. See, I'm going to take the liquid nitrogen I have left. Go ahead. I'm going to take the liquid nitrogen I have left here and pour in the bucket like this here. There we go. Then take this here. Take this here. And take this here. There we go. Go ahead. See. So, okay, okay. So for Iris, having done such a wonderful job there, I'm going to reward her with this very nice. The youth of America. I was going to reward her with this very nice flower for doing such a wonderful job. But I think I said a little soap. Does that look like a little soap to you? Does she still deserve the flower? I don't know. Oh, wait a second. The way to thaw my frozen heart. Thank you very much. Thank you. Thank you. You're done. Thank you. Okay, oh boy. See, the idea behind this is pretty straightforward. By taking and mixing that soapy water with this nitrogen I have left here, we see some bubbles made, but obviously it's very soapy water. Just going to have to kind of do this on the count of 3 type thing. A couple things before I continue. I have a Facebook fan page, a website. There's some neat videos up there. There's a slow motion of that box blowing up. Really neat. iPhone 6s record the audio at the same time, so it's kind of neat that way. I have a blue flyer here. Feel free to take one. Some fun information about cryogenics and me and all that. But now I need to check a couple things. The first thing I need to check is, are you ready? Yeah. The second thing you need to check in this case is, am I ready? Yeah. Okay, we obviously have to try that again, okay? Are you ready? Yeah. Am I ready? Yeah. How come I heard lots of yeah? Some type of communication problem there? Oh, I forgot, you're kids. You don't know the word no. So, on the count of 3, 1, 2, 3. Oh boy, oh. Oh, it's on? Okay, oh boy. Oh boy. I guess I'm gonna have to change my name to Mr. Bubbles here, okay? Oh, that one's already taken, right? I always like to be sure that whenever I do one of these demonstrations, that you get to leave this little demonstration with something. You kids get to leave, and it's not a shower like I just got. What you're gonna get to leave this little demonstration with is a little science homework assignment. Actually, kids, I would almost be willing to bet you that you would have a hard time not doing this homework assignment. See, your homework assignment has to do with where I work, FermiLab. FermiLab's claim to fame is that we have some of the world's most powerful particle accelerators. We actually have one particle accelerator that shoots the particles right through the Earth to Minnesota. So, how many of you have a particle accelerator at home? I have 5 in my house. I imagine you have one. So now the question is, what in your house obviously is a particle? So what do you think you have in your house that's a particle accelerator? I'll make it easy on you. You watch it every day. Your TV set, your cathode ray tube's an electron gun. It accelerates electrons up to bombard. So your homework assignment, kids, is to do what we do there at FermiLab, and it's not watch TV, okay? Is to go home and operate your particle accelerator. No, don't blow it off. Just operate it. Turn it on, turn it off, change the channel. Okay. So I hope you enjoyed the show, and I hope you learned a little something along the way. So thank you very much.